Alright, so first one, pulling a sled without friction, the tension force is going to make an angle. Let's say a boy uses a rope to pull a sled with his sister in it over a frictionless surface. The mass of the sled and the sister is 10 kilograms. The student causes the tension to be 100 newtons at an angle 37 degrees from the horizontal. What is the acceleration of the sled? First things first, we're talking tension, so we're talking forces, so we're talking free body diagrams. Start with the easy one. Then we have the tension force and the one that will get forgotten, the normal force, because the sister's on the ground. Don't forget that. And don't forget to label. It has to have an F of some kind here. So mg is okay for the weight. Why is normal force less than the weight force? I thought the normal force always equals mg. Normal force only needs to prevent the sled from falling through the ground. With no other forces, then the normal force is going to cancel out the weight force. But here we have a tension force that has a vertical component. And you can see if we break this vertical component up, it's 1, 2, 3 boxes up, plus 1, 2 of the normal force, also up. That should equal 5 boxes down. 1, 2, 3, 4, 5 down. So that all of the ups cancel all of the downs. The normal force has some help. There's a component of the yellow tension force helping lift up on the sled. So the normal force doesn't have to apply as much force to balance the weight. Now let's draw an acceleration vector near the free body diagram. We can guess that the acceleration will probably be to the right, right? It looks like the boy's running to the right, probably not running backwards because you can't push with a rope. There's our acceleration vector. Now any force that is neither perpendicular nor parallel to the acceleration needs to be made into components. So parallel to the acceleration is going to be exactly to the right. Do you see any forces exactly to the right? Perpendicular is going to be up and down. Do you see them up and down? Yes. Normal and the weight. So these don't need to be broken into components. But this one that is neither perpendicular nor parallel needs to be broken into components. So the components, one needs to be parallel to the acceleration and one needs to be perpendicular to the acceleration. The one parallel is what's causing the motion to go to the right? That's the force doing the work. Our angle is from the ground, so that means this side is the adjacent side of the triangle, which means ft cosine theta here, and then ft sine theta in the vertical. Balanced force equation. Forces perpendicular to acceleration, balance, normal, and ft sine theta are both up and weight is down. So we get normal force plus ft sine theta equals mg. Forces parallel to acceleration make ma. Forces against acceleration count as negative. The only force parallel to acceleration is ft cosine theta. So we get the equation, stuff that makes it go, minus nothing, no friction here that we're dealing with, equals mass times acceleration. Then we can use the net force equation to solve for the acceleration. Acceleration of 8 meters per second squared. That's it.